what's she doing, Joe?
You know how she gets her food from the bowl and runs to the rug and chomps it?
Yeah.
She was doing that while Mom was on her call.
And you're on the beginning of my pre-calculus video now. For eternity. That is on YouTube. Great. Good morning, Miss Kelsey.
Good morning.
How are you feeling about chapter 6 so far?
Yeah.
Have you looked at the practice test that I put in my math lab yet?
Yes, and don't look at the grade for that because I was just trying to see like how this was going to work because some of them I didn't know. Like,
right. Well, we have 2 sections we haven't even covered yet, but
Yeah.
No, you're not going to have a grade for that. And Wednesday I'll answer any questions you have from it. And if you can do what is on the practice test in my math lab, you can do what's on the real test in my math lab. And it's, of course, open book. So you have your addition, subtraction formulas, your double angle and half angle formulas. You just need to know how to use those. And let's see, double angle, half angle, sum and difference formulas. That part of the test, excuse me, is pretty easy. I'd say the 2 hardest things in the test are solving equations, which I've been telling y'all all along. Solve all the trigonometric equations you can get your hands on, including those on the practice test for you printed from Momentum, as well as the ones that I put in my math lab.
Mm-hmm.
So solving equations, and then the inverse trigonometric function section 6.6 takes some practice. Those are the 2 hard things. What we're doing today and tomorrow, in my opinion, those are easy. So 6.2 and 6.6 are the 2 big ones you need to work on. Mr. Evan, good morning.
Good morning.
Miss Carly? Carly, can you hear me? Oh, darn. Miss Carly's, okay, no, Carly's good. She can hear us. She just doesn't want to talk to us. All right. So do you have anything that you need to ask me from 6.6 before we start 7.1?
I think I'm good.
Okay. Miss Kelsey, are you good on that?
Yeah, I don't have any questions.
Okay. All right. That was for calculus and we didn't need it, so 7.1. The last 2 sections of pre-calculus and the last 2 sections of trig extend our ability to solve for missing parts of a right triangle or missing parts of a triangle from just right triangles to any triangle. In previous sections, we found how we could use, for example, excuse me, if I give you a right triangle with some angle alpha, and I tell you, let's say the opposite side is 7 and the hypotenuse is 12, then how could you find alpha in that situation? If I tell you this is a right angle.
Can we use sine of alpha equals 7/12?
Absolutely. And if we had sine of alpha equals 7/12, how would we find alpha?
Inverse of sine?
Yeah, we'd say alpha is inverse sine of 7/12. And once we knew alpha, how would we find beta if we call this beta? Think, think, think.
Would you use cosine then?
You wouldn't even have to. How many degrees are in any triangle?
180.
And you know this one is something. We didn't punch it on the calculator, but we could have. We would just subtract alpha from 90 degrees, and that would give us beta. Or we could say 180 degrees minus the 90 that we know minus the alpha that we found out. That's how we could find beta. How could we find, let's call this side B, how could we find B?
Pythagorean theorem.
Yeah, absolutely. B would be the square root of 12 squared minus 7 squared. I thought I was making up a Pythagorean triple, but I didn't. Yeah, that wasn't a Pythagorean triple. So we can, if you give me two sides of a triangle and you tell me it's a right triangle, you've given me one of the angles, then I can find all the missing parts. But what I have not been able to do up to now is if that was not a right triangle, then, or yeah, if that was not a right triangle, then I couldn't use sine of alpha is 7/12. I'd have to have a different way to find alpha and beta. So the different way that we're going to solve for the missing parts of an obtuse triangle, not a right triangle, but any other triangle, an obtuse triangle, we have two tools, the law of sines and the law of cosines. The law of sines is section 7.1 and the law of cosines is section 7.2. And we need to all be in agreement in how we're going to label our triangles. It doesn't matter which side you call A, which side you call B, which side you call C. There is no hypotenuse because this is not a right triangle. But if you label your sides A, B, and C, then we have to agree we're going to let alpha be the angle opposite A. We're going to let beta be the angle opposite B, and we're going to let gamma be the angle opposite C. Now that reminds me, in my math lab, they don't use the notation alpha, beta, and gamma. They let capital A be the angle opposite side A, and they let capital B be the angle opposite side B, and capital C be the angle opposite side C. And I have that as a pop-up in those problems on the practice test. The notation's just slightly different. The law of sines says, let me back up, start that sentence a different way. So there's 6 parts of this obtuse triangle. There are 3 angles and there are 3 sides. You can use the law of sines whenever you're given one complete ratio of a side and the angle opposite it, and then any other piece of information. If you have A and alpha and something else, or if you have B and beta and something else, or you have C and gamma and something else, you can solve for the three missing parts using the law of sines. When you don't have that, you have to use the law of cosines, and that's tomorrow. The law of sines says the sine of the ratio of the sine of any angle and the side opposite it is equivalent to the ratio of the sine of any other angle and the side opposite it. So sine of alpha over A, that ratio is the same as the sine of beta over B, is the same as the ratio of sine of gamma over C. Or you could flip all those ratios upside down and the equivalency would still hold. So you can use the law of sines in two different situations. Really, it's easier for me to think of one situation. If you have any one of these three ratios and then any other piece of the puzzle, you can find the missing parts. But we need to talk about when we're given two angles and any side, or two sides and an angle opposite one of them. This is the easy case. If we have two angles in any side, we're always just going to get one distinct triangle as an answer. For example, number 2. Let's see what we're given. Darn it. Oh, I have it. I thought I hadn't printed. Page 488. Number 2. We're given beta is 25 degrees, gamma is 41 degrees, and B is 170. We don't know the units on B. It could be inches or centimeters or miles. We don't know. But here's our one complete ratio. We have a side and we have an angle opposite it. If we're given gamma, what could we find next using the law of sines? If I have B and beta and gamma, which side could I find next?
C?
Yeah, you could find the side opposite gamma. Now, you don't have to draw these, but if it helps you, you absolutely can. You know, all of my triangles are going to look the same. Nothing's going to be to scale. But let's say we had this, which is not a right triangle. And we found out this was 41 degrees. And that's our gamma. Then opposite gamma is C. Opposite beta is B. Then that means this other angle is alpha and this other side is A. And we want to find alpha, A, and C. I like to put, with the law of sines, you can have each one of these ratios, the angles on top or the sides on top. The way I decide which one to put on top is the thing I'm looking for. If I'm looking for C, then I'll put the sides on top. I'll put C over the sine of gamma equals B over the sine of beta. So that all I have to do is multiply both sides by sine gamma, and I'll have the C by itself. Let me go ahead and substitute numbers there. We know gamma is 41 degrees, and B is 170, and beta is 25 degrees. So C is just going to be multiply both sides by sine of 41 degrees. And punch it on the calculator. I'm just going to tell you what I got there. I got 264. And again, that's a side, and we don't know the units. Now, that's one of the things we were looking for. Once we have that, tell me how to find another piece of that puzzle. The other two things we're looking for are A and alpha. Do you see how we could find alpha?
Could we add up the angles and then subtract it by 180 again?
And instead of, just because you're going to be a math teacher someday, instead of saying subtracted by, is subtracted from. So alpha would be 180 minus 41 minus 25. And that is 114 degrees because it's an angle. All right. I was given 3 things. So far, I have found 2. How can I find A? Somebody tell me why I can't use the Pythagorean theorem to find A.
It's not a right triangle.
Because it's not a right triangle. Very good. Pythagorean theorem only applies to right triangles. So if I can't use that, how can I find A?
Could you do A over sine 114?
Absolutely. A over sine of 114 degrees. I could use B over sine beta again. So 170 over sine of 25. I got that to be approximately 367. There's a note in the book about rounding. When you're solving for missing parts of a triangle, you express your answers to the same degree of accuracy as the information you were given. So if we were given gamma and beta to whole numbers, we should express alpha as a whole number. If we were given, it's hard to tell with this B if that's rounded to the nearest whole number or could be rounded to the nearest 10. We really can't tell. The last significant digit here is in the tens place. So I think we would assume that that's round to the nearest 10th. And if so, we would round C to 260 and A to 370. But I don't want you to worry about that on the test. In my math lab, it tells you what to round to. All right, that is the first case in which we used the law of sines. We were given 2 angles and one side. The side we were given had to be opposite one of these 2 angles. And so what about when we're given 2 sides and an angle opposite one of them? Now there's something that I don't think I copied from the book. I think, well, if you have your book, it's on page 484, figure 4. I don't have that with me, but if you're given 2 sides and an angle opposite one of them, there are actually 4 possible things that could happen. Let's say if I give you this length and this length and an angle opposite one of them. Let's say I have a little bitty short side and a long side. This is not going to work very well. And I need that picture from the book, gosh darn it. What's bugging me? Two sides. And let's say I give you this angle. I actually think I'm going to have to pull that up. Hold on just one jiffy, because I'm going to have a hard time explaining this without pointing. Give me just a jiffy. That's page 484. My computer is so slow, but I'm almost there. Y'all, I'm sorry, I should have had this page printed. Oh, snap. If y'all want to take up a collection and buy me a new computer, you can. One more jiffy. I have my pre-cal book open. I just got to get to the right page. 484. Lord have mercy. All right. And the challenge is making you see it. Can you see the book now?
I can.
Okay. All right. Figure 4 is what I was trying to pull up. And let's see, Miss Carly. Yes, Miss Carly can see the book. Figure 4 was what I was trying to pull up, and you're just going to have to watch my cursor moving. If I give you a side A, a side B, and an angle alpha, and tell you to put these together in form of a triangle, it's possible that alpha is big enough that side A can't be made to connect with the opposite side. You got a long straw, a short straw, and an angle opposite the short straw. It could be that the short straw is just not going to touch the base of the triangle. So one possibility in part A, if the arc does not intersect the x-axis, sometimes you just have to say there's no solution. There's no triangle that I can make using the information you gave me. Part B shows you that if you give me a long straw B, a short straw A, and the angle opposite A, it could be that A is just the perfect length to make a right triangle. That's the second possibility described in part B here. If the arc is tangent to the x-axis, then one of your possibilities is you have a right triangle. It's the part C and D of that illustration that we call the ambiguous case. Sometimes the length of that side A can be just perfect for making two different triangles. That's a possibility. I could get two different answers or build two different triangles with the information you've given me. And then the fourth possibility is, looks like it could be the ambiguous case, but only one of the triangles actually works. So we're going to be given two sides and an angle opposite one of them. We have to figure out which one of these four scenarios is going on. No solution, one solution, and it turns out to be a right triangle, or two solutions, or hey, it looked like there could be two, but only one of them works. Now, that's the picture I wanted to show you. And let me close that, and let's talk about how we determine which one of those four scenarios is happening. Number 8. We're given alpha is 27 degrees. C is some side 75 units. I don't know what the units are. And A is 34. How do I know, if these problems are all mixed together on the test, how do I know that I can use the law of sines on this one?
Because you have alpha, angle, and A.
That's right. Yeah, I have one side and the angle opposite it, and then any other piece of information, I can use the law of sines. If I'm given alpha and A and C, what piece am I able to find first using the law of sines?
Gamma.
Yeah, I can find the angle opposite C. So if I'm looking for an angle when I use the law of sines, I'm going to put my angles on top. I'm going to say the sine of gamma over C is equivalent to the ratio of sine alpha, which is 27 degrees, over A. And so sine of gamma would be 75 sine 27 degrees over 34. Now, I want to punch that on my calculator, but I don't want to round it. Let me grab my calculator. $75, make sure make sure your calculator's in degree mode. I had mine in radian mode. Degree mode. 75 times I have the fabulous backwards calculator. I have to enter the 27 before the sign, and then divided by 34. Now, I want to keep all of that on my calculator, but what I'm going to write down is sine of gamma is approximately 1.001, let's call it 145. If that's approximately what the sine of gamma is, how do we find gamma?
The inverse.
Yep. Now, I don't know if y'all have your calculators with you or not, but I still have all of that on my screen. And then I'm going to do inverse sine is second inverse sine. What does that mean? I mean, I punched something wrong, or that's not possible, or what? What if I just ask you to squint and solve? Tell me the angle on the unit circle whose sine is 1.00145. Sine is your y value of a point on the unit circle. What do we know about the y values of all the points on the unit circle? Or I could say it this way. What do we know about the range of sine, the graph of sine? Ooh, Miss Carly's got it. Ooh, and you said it beautifully, Carly. There is no angle whose sine is greater than 1. Good job, especially since you had to type it. Sine is always a number between -1 and +1, and I've just asked my calculator to find an angle whose sine is bigger than 1. My calculator is telling me it can't. Which one of the 4 scenarios that I just mentioned do you think is happening here?
The circle is enclosed.
Yeah, there's just no such triangle. If I gave you, I'm sorry, Evan, what'd you say?
I said circle, but I meant triangle.
Yeah, I knew you did. If I gave you a 34-inch straw and a 75-inch straw and told you to make a triangle with those 2 straws such that the angle opposite the 34-inch side was 27 degrees, it would be that first scenario that we saw. The second straw is just too short to connect to the base of the triangle. There is no triangle that satisfies those conditions. So we could describe when we're going to get no triangle for an answer just by saying whenever the right-hand side here turns out to be greater than 1 or less than -1, there's going to be no such triangle. All right, let's see what causes another one of those scenarios to happen. In number 10, we're given alpha is 27 degrees 30 minutes and C is 52.8 and A is 28.1. So I know I'm looking for B and beta and gamma. That's the 3 things I want to find. How do I know that I can use the law of sines on this problem?
Because you have the alpha and the eigen, which is opposite of each other.
I have one side and an angle opposite it. And then I have another side, so I can find the angle opposite it. I can find sine of gamma again. Sine of gamma over C equals sine of alpha over A. So sine of gamma is going to have to be 52.8 sine of 27 degrees 30 minutes over 28.1. All of a sudden, I haven't used this calculator in so long, I've got to, hey, if I have forgotten how to enter 27 degrees 30 minutes on my calculator, what would that be as decimal degrees? 27 degrees 30 minutes would be what? How many minutes are in a degree?
Would it be 27.5?
Absolutely. Now I just got lucky, otherwise I'd have to sit here and remember how to enter minutes on my calculator. I'm just going to enter that as 27.5 degrees. And then the sine of that times 52.8 divided by 28.1. And I've got approximately, I'm going to keep all the digits on the calculator. I don't want to round anywhere in the middle of the problem, but just to have something to write down, I'm going to say that's approximately 0.8676. Is there going to be an angle whose sine is 0.8676 somewhere on the unit circle? Somebody just say yes.
Yes.
Okay, thank you. How many angles are there on the unit circle whose sine is 0.8676? How many times on the unit circle is your y coordinate going to be almost +1? In what 2 quadrants do you have angles whose sine is positive? Mr. Evan, sine is your y coordinate. In what 2 quadrants are your y's positive?
1 and 2.
Yeah, one maybe about right here and one maybe about right there. This is where we have two possible triangles. This would be one of our triangles. This would be the other possible or other triangle. So whenever we get sine of gamma is something between -1 and 1, we know that there's a solution. There may be two solutions. Just going to say two possible triangles. So how can we find, if there are two possible triangles, how can we find gamma for the first one? I'm just going to call it gamma 1. How would we find it?
Could you do the inverse sine?
Yep, and that's why I kept all these digits on my calculator. I don't want to do any rounding in the middle, so I'm going to have all of those, and then inverse sine is 60.18. Now, the only angle we were given is alpha, and alpha was given to us in degrees and then maybe to the nearest 10 minutes. So I'm going to say that's decimal degrees. I'm going to say decimal degrees to degrees, minutes, seconds, second, and that. And then that's 60 degrees. Oops, you can't see that. 60 degrees, and to the nearest whole minute, it would be 11 minutes. Or if this is rounded to the nearest 10 minutes, then you would report alpha as 60 degrees, 10 minutes. Don't worry about that rounding thing, though. My math lab's going to tell you what to round to. I'm going to say if that's to the nearest 10 minutes, then gamma 1 is 60 degrees, 10 minutes. That would be this angle in the first quadrant. Now, how would I find this angle in the second quadrant? If this is 60 degrees, 10 minutes above the x-axis in the first quadrant, how do I find the angle that's 60 degrees, 10 minutes above the x-axis in the second quadrant? How many degrees does it take for you to get all the way around to the x-axis? I don't know if y'all went all mute at the same time or not, but if that's 180 degrees and this is about 60 degrees, then that's 120 degrees. You remember when we were doing inverse trig functions and the directions said find all possible angles? Well, 60 degrees above the x-axis in the second quadrant is 120 degrees. Or if the reference angle is 60 degrees, 10 minutes, then in the second quadrant, the angle would be 180 degrees minus 60 degrees, 10 minutes. Or 119 degrees, 50 minutes. So we actually do have two triangles that meet these conditions. And we're going to have to find the missing parts for the first triangle and the missing parts for the second triangle. Now, because y'all have gone, ooh, Miss Carly said something. Yes, Carly, you're right. You were right. Subtract the 160 from 180, right? Okay. Evan and Kelsey, are you still with me? Does that make sense?
Yes.
Okay. let's find the two other remaining parts of the first triangle, and then we'll find the two remaining parts of the second triangle. For the first triangle, we have alpha, we have gamma. What would it be easy to find now? If you know two of the angles. How could we find beta 1? Subtract the two angles that you do know from 180. I got that to be 92 degrees and 20 minutes. So they only, let's go ahead and find beta 2. Just 180 degrees minus 27 degrees 30 minutes minus 119 degrees 50 minutes. I got that to be 32 degrees 40 minutes. So the last two things we need are, we have A and C, we need B, little b1, little b2. What information do we have that we could use to find B1?
We have the angle of beta.
The angle of beta, you have, yes. So how could we use that to find B1?
You can say like sine of beta, which is
Right,
2 degrees and 20
right.
over b.
So you're gonna have to go back to law of sines.
Mhm.
Say B1 over sine of beta 1 equals, it's better to use the information you're given than some information that you've rounded. So I'm going to use the A over sine alpha. And just for time's sake, I know you could find B1 now. I'm going to tell you what I got. I rounded it to the nearest 10th because A and C were rounded to the nearest 10th. I got that B1 is 60.8. And using the law of sines, I got B2 to be 32.8. So that is the third scenario we mentioned when I showed you that picture from the book. The first scenario was no triangle. The second scenario was actually, it turns out to be a right triangle. What do you think you would have on this line that would cause you to know, hey, this is a right triangle?
Would it be 1 or -1?
Yes, if you had sine of gamma is 1 or -1, then you would have a right triangle. The third possibility was you got two triangles, and the fourth possibility was I thought there were going to be two triangles, but it turns out that only one of them works. So let's do that as, how are we doing on time? Ooh, we've got 5 minutes. I've got to show you 16 so that you will know what causes you to think could be two triangles, but it turns out just to be one. That happens on number 16. and I'm going to go quickly through this. Since we have C and gamma and A, we can use the law of sines to find the sine of alpha. Sine of alpha over A equals sine of gamma over C. I'm going to punch that right-hand side on my calculator. Is this no triangle, right triangle, or possibly two triangles? Anybody?
Looks like possibly two triangles.
Looks like possibly two triangles. There's definitely at least one angle whose sine is this, and we can find it by punching inverse sine of that, only I'm keeping all the digits on my calculator and just saying inverse sine of that is 54 point. Since my other angle was rounded to the nearest hundredth, I'm going to round this to the nearest hundredth, 54.88. Dang it. Yeah, that's what I got. All right. So I'm still thinking there's two possible triangles. Something is bugging me. All right. As I'm so good at doing, we're going to finish class on a problem that is bugging me. What's supposed to tell me there's only one triangle is if when I try to find the other one, we're good, we're good. If this is 54.88, then, and that's alpha 1, then alpha 2 would be 54.88 degrees above the x-axis in the second quadrant, and that would be 180 minus 54.88, or 125.12. So I'm still thinking, okay, I'm back on track now. I'm still thinking two possible triangles. And beta 1 would be 180 minus 73.01 minus 54.88. I got that to be 52.11. Y'all find beta 2 for me real quickly and we'll be through. Or just tell me how to find beta 2.
You would subtract 180 minus 73.01 minus 125.12.
What do you notice when you punch that on your calculator? $73 and 125 is 198. I subtract 198 from 180, I'm going to have a negative angle, and that doesn't make sense. So I did have two possible triangles, but when I noticed that my second angle and the angle I was given are so big that there's no room for a third angle, that's when there's only one triangle. I would still have to find alpha and gamma, and I think you could do that with the law of sines, but I wanted you to see an example of how there looks like there could be two triangles until you try to find the third angle of the second triangle, and then you realize just one of those isn't going to work. Now, the thing that we didn't have time to do, and I hate that, but we didn't have time to do the word problems. I've only assigned you the pretty easy ones. Ooh, actually, on the notes, make sure you change this on the notes that you've printed. Make that 7.1 stop at 23, because there were a couple I knew we just wouldn't have time to talk about. But like the other problems we've done in trig, the hardest part's going to be drawing the triangle. Once you draw the triangle, you can figure out how to use the law of sines to solve the triangle. So if you stop at 23, you're only going to have 4 word problems. Y'all try those, and then if you need to see one of them as an example tomorrow, we'll do it before we start 7.2. And 7.2 will be, how do we solve for the missing parts of a triangle when we cannot use the law of sines? And the answer will be law of cosines. Alrighty? Y'all know what to do tonight? Hey, and you've read the email I sent about the test, right? Evan, have you read it?
Yes.
And Miss Kelsey?
Yes.
Okay. And I bet somewhere Miss Carly's saying yes. Y'all work on 7.1 homework and let me know if you need to see one of those word problems tomorrow, okay?
Alrighty.
All right. Have a good day.
You too, Miss Miles.
Bye-bye.